Here I have a bunch of clear plastic objects, but just because we can see through them doesn't mean light travels through them the same way. So we mentioned in a previous video that light is a wave, but what does that really mean? Well, think of a water wave. There are rhythmic fluctuations in the water. So a wave is a disturbance that travels through something, like through air or through water. We can demonstrate what we mean with the Slinky. If we stretch it out, it is at rest and it will just sit here. Not very exciting. But we can cause a disturbance using a motion like this. You can see that it travels all the way down the length of the Slinky. If we make more of these pulses, we can build up a continuous wave. This is what we can imagine that light looks like. There are many types of waves, and the motion through the Slinky is one kind. What kind of waves can you think of? Water waves are one of the most familiar kinds, like we mentioned before. You can imagine the ripples that spread out in calm water if you drop a rock in it. But did you know that sound also travels in waves, but that these waves travel through the air? And light, as we have been discussing, is a wave, but it is made out of something less tangible than water or air. It is made up of electric and magnetic fields. This is a measure of how strongly an electric charge, or a magnet, would be pushed or pulled in the space. Earlier we mentioned that waves can be different sizes, and that this determines the color, or differentiates visible rays from the X-rays that you would use to take a picture of your bones at the doctor's office. But there's another way that light can be different. Let's demonstrate it with a Slinky again. Now we can wave the Slinky in any direction. We can wave it vertically, we can wave it horizontally, or we can wave it at any diagonal angle in between. Since light is a wave, just like the Slinky, it can vibrate in different directions. And light that vibrates in one specific direction is said to be polarized in that direction. These big sheets of see-through plastic are called polarizers. And although you can't tell just by looking at them, they separate out only the light that is waving in one specific direction. That means that if we hold this one like this, it will only let through the horizontally polarized light, or the light that is waving in this direction. So what do you think would happen if we stack more than one polarizer on top of each other? Well, if we line them up, it looks a little darker, but light still gets through. However, as we tilt one, less and less light will make it through. And once they're crossed, no light will make it through. This is because the light that gets through the first one is vertically polarized, but the second one only lets through horizontally polarized light. So no light can make it through both of them. Now, enough of the boring stuff. This is where it gets interesting. Here you can see we have one polarizer set up on a projector. We're going to place another one down on top. Now we're going to rotate it 90 degrees. You can see that the light from the first polarizer is getting blocked now. I have a plastic fork like you would find at a picnic. I'm going to place it between the polarizers. What do you see? Let's take a closer look. Now the fork is colorful, and if I move the fork, the colors change too? Where did the colors come from? Forming plastic into these specific shapes puts stress into it. If we squeeze the tines of the fork, we are inducing more stress, and here we can see the colors and pattern change once more. Like all the demonstrations thus far, the colors come from white light. But something different happens when the light passes through the plastic and the polarizers. This is a different source of color. This is called stress birefringence. But all that big word means is that the stress in the plastic decreases the polarization quality. Meaning, even though the light we sent in was all polarized in one direction, because it had passed through a polarizer, the plastic changed the polarization. Polarization also has other important uses outside of looking at the stress in plastics. Many pairs of sunglasses are polarized, which is what helps them reduce glare, and polarization is also the basis of 3D movie glasses. Most screens on electronics are also polarized, So if you have sunglasses and you want to check to see if they're polarized, you can do this by rotating them in front of a display. If you can see any change, it means the screen and the glasses must be polarized. Let's try it with this laptop. If we rotate the polarizer in front of a blank white display, you should see the brightness almost goes to 0. Now, this effect may be less pronounced on some screens, and it may even show up as a change in color, but you can try this at home. Polarization is also used by geologists who are trying to identify crystal or mineral structures. Many fields use polarization to learn more about the microscopic structures that we can't see.
Today we have shown you some of the secrets of light. Starting with looking at all of the colors that are hidden inside of white light, we talked about how light is used in everyday electronics like cell phones. We reviewed some of the strange and unexpected behaviors of light, and even discussed the light that we're unable to see and how it is used. However, this is just the tip of the iceberg. Applications of light and optics can be found in virtually all modern technology. The possibilities are limitless. Light can tell us a lot about the world, if we learn how to understand it. This, along with all of the other fields of science, have allowed us to develop the modern technology that brings us, as a society, into the future. If you continue to study science and try to understand the world around you, you too can contribute to the science and technology that can change the world. Thank you to all of you for watching, and we hope that you learned something from these videos. If you found these demonstrations interesting, maybe consider a career in optics or another field of science or engineering. Julian and I have put together these videos as our senior design project. 6 of these demonstrations are from the original Optics Suitcase, which is an interactive presentation package, which was designed by the Rochester section of the Optical Society. So a big thank you to them for the materials and just for making this project happen. If you are an educator and are interested in physical Optics Suitcase materials, please visit their website at www.osarochester.org. We also want to acknowledge the OSA Foundation, who has supported the Optics Suitcase program since its conception, as well as thank the Institute of Optics at the University of Rochester for access to materials and for their support through the production of this video series. So, I hope that you keep learning about science, and above all, stay curious about the world around you.